One of my favorite movies of all times is The Matrix, and one of the major characters of that particular movie is Morpheus. And one of the statements that Morpheus makes in the movie is, the body cannot live without the mind. This is actually a great way of understanding and summarizing how the CPU functions with a computer. The CPU is the computer's brain. It does all of its thinking and all of the processing that takes place inside the box. Without it, the lights may blink, the drives may spin up, but the light will be on and no one's home. It essentially just becomes a big paperweight. By being able to take a closer look at processing technologies and how they've progressed, we can explore the nuances of what it takes for a computer to truly think.
As with a lot of things, you need to understand how processors are constructed, how they are put together, and how information flows through them, and that's part of the job of looking at processor architecture. First, let's just take a general look about how processors, whatever the type or speed, generally operate. Processors work through a number of different tasks over and over again, and there's essentially several cycles involved. One is the fetch cycle, where it's actually fetching a particular instruction so it knows what to do. It then decodes the instruction, understands what it means, then it executes or puts into practice what that particular instruction is, and then it stores the results. And of course, the whole process starts over again. So this set of operations happens time after time in a number of very rapid cycles, but this is essentially what the processor does. It gets instructions, it understands the instructions, it executes the instructions, and then stores whatever the result is. Now, processors, or CPU as they're sometimes called, central processing unit, have a number of different internal components. These aren't going to be generally visible to the naked eye simply because there are so many transistors and circuits within a processor. But first you have an input-output unit. Remember we talked about front-side bus? It connects to the north bridge. There's also an input-output unit, and this manages data and instructions entering and leaving the processor. Next is a control unit, and pretty much manages all the activity inside the CPU. You can think of it as sort of a police officer directing traffic. Then you have the ALU, the arithmetic logic unit, which manages all the calculations inside. And then there are some memory registers, a lot like RAM, internally. And then you have cache, and then the internal bus, which essentially connects all these different components together. And this is the basic construction of the inside of the CPU or processor. We're going to talk a little bit about cache memory. Cache memory is actually very fast memory that's a part of the CPU in one form or another, and it's used to store frequently used data and instructions. Now, as we talk about cache, you can either describe cache in layers or levels. And generally you can use either one. So level 1, level 2, level 3 cache and things like that. But generally the terms are interchangeable, just as a point of clarification. First, there is level 1 cache. It's the fastest and it's right on the die of the processor itself. Next you have layer 2 and layer 3 cache. Rather than being on the die, they're adjacent or off the die, which means they are still very, very rapid, but not nearly as rapid and accessible as level 1 cache. And then, of course, you have the connectivity to the rest of the system, just as we've discussed before. One of the things that you will see in terms of processors is you're going to hear about speeds or measurements. But processor speed is measuring the internal speed of the CPU, and it's measured in hertz. Here's just an example. You have one CPU, evidenced by the very practical looking vehicle. You'll see it moves along. It's great, but it's not very fast. And you have the sports car type of vehicle. Notice how much faster it goes. And the idea here is that not all processors run at the same speed. Some run faster, some run slower. Generally, the newer a processor is, the faster that processor is. And just as you have speed limits on the road, you have speed limits of a processor, which are basically the same thing, just looking at it in different contexts. And the speed of a processor is controlled by a crystal that actually tells it what its maximum recommended speed is. There is something called overclocking, so processors can run at higher than their rated speeds. But while that's popular for a lot of systems like gaming systems, it can also reduce the life of the CPU as well. And there's also processor width. So you have speed, which is in megahertz, and then you have processor width. And in this case, it refers to the maximum width of the CPU structure. The ALU, registers, address bus, data bus, and so forth. Now, in terms of 32-bit and 64-bit systems, They actually have a limit on the amount of addressable memory that they can work with. 32-bit systems, for example, is 2 to the 32nd power and yields a limit of 16 gigabytes. 64-bit systems, on the other hand, 2 to the 64th power, can handle 16 exabytes of RAM and memory. Now keep in mind that these are hardware-based limitations. They have nothing to do with the operating system. Actually, the Microsoft Windows operating system is actually limited in the amount of memory it can work with. For instance, there's a 16 terabyte limit when it comes to certain types of operating systems, so keep that in mind. Another important concept to understand with regard to processors is the idea of threading. So you have the basic construction of the CPU here, and let's first talk about single threading. So you have one task that's running and another task that's going to be running as well. What the system does is it takes all the data from task 1 and executes it like so, taking it through the system, through the execution core and back out. But the second task has to wait until the CPU has finished executing, and only then does it have access to the processor. So essentially it has to wait in line. This is called single threading, meaning a single thread of instructions going through the processor. Then there's another method. It's sometimes called multi-threading. We see a situation very much like the one we introduced just a moment ago. Task 1, task 2. But notice this time, you have both going through the system at the same time. More than one thread is being executed by the CPU. It's essentially multitasking. It's parallelizing the computation process. Now, the operating system interacts with these virtual processors, so to speak, but it divides work between these two virtual processors, and you also have to have an operating system that supports hyperthreading. But this, as you could see, would vastly increase the efficiency and speed by which instructions are being executed by the system. Hyperthreading, simply because you can have more than one running through the CPU at the same time. Computing continues to expand in terms of capabilities, speeds, and technologies. Just as you saw the vast increase in efficiency between single threading and hyperthreading, doesn't it make sense that to find a way to be able to have multiple processors at the same time? And that's actually become quite a topic among computing and virtualization professionals today. First, we'll look at the single core processor, which is essentially what we've been looking at all this time. So you have the CPU, you have the core, you have your cache memory. You essentially have all the elements that we've been talking about in terms of just basically a single processor with one core. A multiple core processor, on the other hand, you actually have two distinct CPUs within the CPU. So on one die, you have more than one. And this not only allows for hyperthreading per core, but also allows these cores to work together to be able to do multiple things at once, even within their own construction. So you have separate level 1 cache and level 2 cache, but the layer 3 cache is shared. And this allows for multiple cores to be able to interact together to increase efficiency. You can also have multiple processors. So imagine you have multiple processors with multiple cores that they can then execute multiple instructions because of hyperthreading. And you can see how this cascades into an incredibly fast machine. Now, the motherboards have to be compatible with multiple processors. The operating systems have to be able to support that. And this is actually what's called symmetrical multiprocessing. Again, being able to do things at a greater speed and efficiency than ever possible before. Processor in one slot and in the other, and they work together, even with multiple cores, to accomplish this vastly increased capacity.
So now we're actually ready to put the processor in the system. You can actually see this uses the land grid array that we talked about, and it actually goes in this socket right here. So what we're going to do is we're going to gently open the socket. Very simple procedure. And we want to make sure that the pins are down. Also helps to have it going in the correct direction. Place it gently in the socket. Place the window down. And then we push the lever down so that it actually properly seats inside the computer. And there you have it.
So let's just go over a few terms. So a core, this is the part of the processor that performs the reading and executing of instructions, much as we talked about in the beginning. Hyperthreading is a technology that allows a CPU or processor to multitask, to actually do more than one task at a time. For any of you that can remember back to the days of DOS, that was almost like a single threading system, whereas with Windows you were able to do multiple tasks at once. It's the same idea. Overclocking, this is a method used to increase the clock speed of a CPU, essentially over its rated speed. And then the cache, which is an area of extremely fast memory accessible exclusively by the system processor. Most processors have 3 levels of cache memory. Remember, level 1 is on the die, level 2 and 3 are off die.
Great stuff, isn't it? One of the ways that you can keep this firmly fixed in your mind is, in fact, think of the computer processor as the mind. It does all the thinking for the computer and allows it to do all of the different wonderful tasks that we expect it to, just like your brain and your mind allows you to be able to participate in this learning. Great way to be able to start out with understanding processors. Thank you so much for watching. We have a lot more to cover.